Then I explain what's happening with our. Yeah, it's recorded now. So we start our seminar. It's a first seminar in spring semester. Let me introduce our speaker today, Shimi Malenica. Shimi Malenica has a naval architecture degree from University of Zagreb, and he obtained his PhD degree in hydrodynamics in '94 from Paris 6 University. After graduation, PhD graduation, he joined Bureau Veritas. This is certification society, French certification society, where he is still employed. He has been a head of hydrostructure section team in the research department for a long time, and from 2008 he is deputy director of research department in Bureau Veritas. His main field of research concerns the different aspects of fluid structure interaction. He is leading several national and international research projects on these topics. He is working in both theoretical and practical aspects of ship and offshore hydrodynamics. He published 150 papers in both international scientific journal and specialized conferences. He is associate professor at the Faculty of Mechanical Engineering and Naval Architecture at the University of Zagreb, and from 2016 he is the corresponding member of the Croatian Academy of Sciences and Arts. I believe with great achievements and recognition of contribution Professor Malenica to the field of that research. Malenica was the coordinator of FP7 project with title Tools for Ultra-Large Container Ships. This project was led by Bureau Veritas with the such huge shipyard as Hyundai Heavy Industries as a part of that project. We also, UEA was part of that project. That's why I'm mentioning this project in particular. And we benefited from guidance provided by Bureau Veritas and Shimi to us in terms of practical applications of our research, making sense to our mathematical formulas. So Shimi, it's now we start your seminar. Please, may I ask all participants to switch off their videos, so no videos so far, and also microphones. That is the for the teams. Then the presentation will be for 25-50 minutes. That is standard, and then we have time for discussions, say 10 minutes, but actually time for discussion is not limited, so we can stay as long as we can, talking about everything at the end of our presentation by Shimi. So Shimi, please start, and I'm also switching off my camera, okay, and my microphone. But before I switch off my microphone, could you please share your slides?
Yes.
Yes.
Can you see it?
Yes, I see it. Yeah, perfect.
Just now. Do you see just the presentation or?
No. Now I see the previous one was the right one. Yeah, that one. Yes.
Okay.
Yes, please start.
Okay, thank you, Sasha, thank you for this introduction. I'm glad to be able to speak at this series of seminars. This is the work which has a quite big practical importance, and it's kind of starting step toward the solution, hopefully in the near future. The work was done in collaboration with the University of Zagreb, Bureau Veritas, and University of East Anglia, Professor Korobkin and Tanya. So we all participate in some way. So this is the content of the presentation. I will say first something about why we are doing all this. Then I will briefly present the analytical solution, which was provided by Tanya and Sasha. Definition of the test cases, which we choose to work on. Describe the numerical approach and the numerical models which were used, and then present and discuss the results. So this is the context of the where the work we were doing is meant to be applied. So this is all sort of impact situations. These are some videos of the large-scale tests on kind of sloshing impact on the corrugation corrugated containment system. So this is just to show how complex is the problem, and what we are willing to know are the stresses in the structures at the end when these impacts occur. Sorry, another type of conditions where this can happen is what we call green water impact on the deck superstructure. Sorry, another type of things is the impact under deck impact on the semi-submersible, and all sort of impacts where we have a very strong hydrostructural interactions and very large pressure forces exerted on the structure. So physically, the problem is complicated because many physical effects are involved in the problem. So fluid flow, sometimes we can consider flow as incompressible, sometimes compressible. Compressibility can matter. On structural size, we prefer to work with the linear type of structural response, but that's not always possible. We should sometimes involve some nonlinear behavior of the structure. And on the interaction side in between fluid and structure, we have several possibilities to do it, either fully coupled, what we call hydroelastic, which is very complex and we try to avoid it, or quasi-static, or kind of mix of quasi-static and dynamic, which we call quasi-dynamic, in which we consider just the structural dynamics. On numerical side, the theoretical models on both sides, on fluid and structure, can be very complex, and as well as the coupling procedure, which can also be quite complex. And then when we talk about the purely numerical method, we have some convergence issues. So the objective of this study was to investigate the possibility of the coupling CFD and finite element, CFD for dynamic loading and finite element code for modeling the structural response. On the dynamic side, we tested several methods, what we call ghost fluid method or classical method. We tested the simulation, compressible and incompressible. On structural sides, we have in-house beam model, which we call Diana 2, which is used in several ways. That was very helpful because we have full mastery of this software because it was written in BV. On coupling side, we have two type of approaches. One which I call direct, which means at the level of the finite elements, and we have modal approach, which is which consists in the coupling through the modal superposition. So in all cases, the Diana 2 beam model was used as a structural solver. But what we should understand is that this coupling is a general coupling, because we can easily replace, everything is done to easily replace the Diana 2 with software like Nastra, Abacus, or whatever. So analytical solution was provided by Tanya Kapasheva and Professor Koropkin. I will just briefly explain what is done there in order to better understand what we are comparing. So the coupling is done under Wagner assumptions, and structural model is the Euler Bernoulli beam with simply supported boundary conditions. And the coupling procedure is based on modal decomposition. So what is interesting to say here is that within the approach they use, the pressure is not explicitly evaluated. So that means that we do not really need to talk about pressure even. But in practice, it happens that we talk only about the pressures. But when hydroelasticity matters, we should not talk. That's one of the points we are willing to raise with this work. So the Wagner model briefly is a simplified linearized model in the sense that we linearize the free surface condition, but it is in fact non-linear because the position of the free surface is not known in advance. So there is a huge theoretical work which was done in the past by many authors, and in particular Sasha, and we end up with kind of this expression for pressure, which is singular at the contact point. So we have the infinite pressure at the contact point, which is physically not acceptable, of course, and but that's the mathematical model. That's we always have some drawbacks of the due to the assumptions we did when building the model. So the maximum pressure can be obtained, and the distribution close to this contact P point can be obtained using some quite non-trivial matched asymptotic expansion analysis, which allows you to properly couple the external internal solution and give a finite type of pressure close to this contact point. So in black line here, we use the solution which was proposed by Professor Faltinson, and in black line, this distribution with corrected distribution is shown. So the red line is something which we would obtain using the pure original Wagner model. So the critical quantity in all this analysis happens to be the velocity of the expansion of the wetted surface, which is denoted here by C dot. And we can see that maximum pressure is proportional to the square of this velocity, and this velocity is proportional. This expansion is velocity is proportional to the impact velocity and inversely proportional to the tangent of the wedge angle, which means as we go closer to the flat impact, this pressure can take huge values. But as we will see, this huge value of pressure does not mean that the structure will that the structural response will be enormous, because this pressure will be absorbed by the dynamics. So what is important to understand about the Wagner model is that one of the main accents of this presentation is on the fact that we should not use just maximum pressure as a quantity which is relevant for structural response. So you can obtain the same maximum pressure, and that's with the very different impact conditions. So you see the impact velocity change from 3 to 70 meters per second. And if you change even slightly dead rise angle, you can achieve the same maximum pressure, but very different pressure distribution. So what matters for the structural response is the pressure distribution, not just the local maximum pressure. So you can see this, what I note, like WQS is the quasi-static structural response, which means applying just applying this pressure on the finite element model, you just obtain this. So you can see that the response can be very, very much different for the same maximum pressure. So meaning that knowing the maximum pressure is not enough. At the same time, if you have what is also important to understand, if you have one constant velocity and you slightly change the impact conditions, which means the angle, your pressure change dramatically, as well as the quasi-static structure response. So using the impact velocity only, we cannot correctly assess the structure response. What we are interested at the end is the structure response. The pressure itself is not so much interesting. It's good to know that it is sharp and it's good to know it, but at the end what we are interested in is the structure response. So this type of pressure, even if this is analytical model, we can say it is just a model. But when you do model test in practice for very small dead-rise angle, you can obtain extremely large pressures. And there was one good paper by Faltinson in which he showed even slightly changing the impact conditions, you can have the pressures locally up to the 50, 100 bars. That's what we measure. But the point is that the pressure is not the only quantity we should look at. So this is the principle of the coupling method which Tanya and Sasha used. I will not spend too much time on this. It's full analytical solution based on normal mode method. So it's very fast converging, and there is no numerical issues. I mean, everything is properly calculated within the theory which we adopted at the beginning. So what we did in this study, the question we asked ourselves is that can we use purely numerical approach, which means in our case foam star or OpenFoam and finite element coupling, to model this kind of situations. So why we do this? Because in practice, we do not have, when we have impacts, as I show in an introduction, we never have a kind of a very clean academic wedge impact problem. It's always something much more complex. And when the geometry of impact and conditions become complex, we can no more use reasonably the simple analytical approach. So we have to deal with more complex numerical methods as this CFD method based on OpenFoam. It's more costly, of course, than the analytical. Analytical, it takes few milliseconds, and CFD takes a few hours. But we have no choice. That's the point. So these are these two graphs shows the different impact condition which we identified, which we tried to model with using this complex numerical coupling. So this is the one. Both graphs presented the response of the dynamic amplification of the response due to the impact on a flat surface using the Wagner type of approach. In the work of Faltinson, it's a bit more complex because they consider the 3D structure, which we should do in practice, of course, but they still use 2D Wagner model by strips. So that's not really a big difference. What is important to understand is that we have three different regimes in which, for which we need to do the simulations. And these regimes are, from numerical point of view, they are very much different. So the different strategy of coupling should be used. So this is the dynamic amplification curve, where we identified three typical regimes. Regime, the impulsive response, when the very short, on the x-axis, on the horizontal axis, there is the ratio in between the duration of the loading and the natural period. So for a very short duration of the loading, we have impulsive response. For when the loading is, duration of the loading is comparable to the natural period, we have dynamic amplification. And where the loading is quite slow, we have quasi-static response, which is the the response we would like, and in practice we would like to use most often because it's the simplest one. In this approach, quasi-static approach, you can simply calculate the pressure and apply it on the structure, and you will have good results. However, for these impact problems, as we will see, these dynamic and impulsive regimes are more relevant. So how to choose these the points, the calculation point. We use this analytical solution to choose the calculation point for the numerical analysis. So we have chosen the plating which is physically close to the plating of the one container ship on which we had some problems. So these are the characteristics of the steel. The length of the plate is 0.8 meter, and then by playing with the different impact conditions, we can identify different regimes we can place ourselves on the different point of this curve. So in total, we took by choosing the reasonable combination of the dead rise angle and the impact speed, we defined in total 21 case for which we did the numerical simulation. So these are, it's very important to correctly choose these conditions and to know in which regime we are placed. So you see here 0, 1, 0, 2, 0, 3, 0, 5, 1, 1.5, and 3. These are the points on the horizontal axis. So when we have 0, 1, we will be close to this impulsive response. When we are 1, it is dynamic, and when it's larger than 2 or 3, it is quasi-static. So on the numerical side, as I said, we used structural model based on Euler Bernoulli beam, which was recently revisited and redeveloped in BV, so that we have something to play with, say, where we can change every detail of the modeling and properly extract any information we need. So both for the direct finite element approach, if we talk at the level of the finite element, or at the level of the modes. So there's something classical, I would say, dynamic structural analysis, but fully mastered by our team. So this is, once you have your structural model correctly mastered, you need to interact with the loadings on the loading side. So quite general interaction scheme was built by my colleague and postdoc from University of Zagreb, in which the interaction between the structure response and the dynamic loading was done through one iteration procedure, which converts actually properly. Most often, in some cases, we need to adjust some things. Everything depends, of course, in which regime we are placed. So these are the natural modes and the characteristic of the finite elements. So nothing special. That's what we have as a result of the structural analysis. This can be also analytical, but here we did on purpose to use the numerical solution, because our objective is to couple later on this OpenFoam and the OpenFoam and the classical generic structural software like Nastran, Abacus, or whatever. So before choosing the characteristics of the structural model, we did some analysis on the convergence of the response based on the number of elements and the number of mode shapes. So this is just to show that this is necessary to be sure that our structure response will converge at the end. So at the end, we choose 20 finite elements along the beam when we talk about the direct coupling, and we use 7 natural modes when we talk about the modal coupling. So this is a few details about foam star. Those who know me know that I'm not expert in CFD, but I understand that we have no choice in some situation. We have to do the CFD. So there are some experts on CFD. They have quite different views on the different strategies which are employed when you need to capture your free surface. So that's one of the main problems, not only in CFD, but in general in dynamics, is to properly capture the free surface. So there are two methods: standard method, which is available in classical OpenFoam, and the newly developed method, ghost fluid method, which was developed at University of Zagreb and which was implemented by Ino within this work. So I will not say too much about the details because I do not really fully understand them, but just to say that there are different strategies. So these are the meshes on which it was, we did also convergence study. In CFD, it is fundamental to do the convergence study because otherwise you cannot, you cannot trust the results at the end. So we did several meshes. So this is the N64, 89, 133, 200, and 300, means the number of the cells along the wedge. So this is just to show that the mesh. So these are the results. So what I choose to present, we did all 21 cases that I shown, and we have detailed results. But what is important, I think, is to look at the different three different regimes which I identified at the beginning. So the case 1 is the impulsive response, case 7 from the table is the dynamic response, and 17 is the quasi-static response. So you can see the comparisons between the pressure and the obtained analytically and the pressure obtained by CFD. You can see that there is a quite, especially in the case of impulsive response, there's quite some differences, which are very large regarding the maximum peak pressure which we obtain during the simulations. But as we will see, even if we have very different pressure, the results in terms of the structural response are quite similar. That's what we were expecting. So this is the same comparison with the forces, just to show that we capture reasonably well using the CFD, the total force on the wedge, even with all these oscillations and numerical convergence problems, I would say, the overall trend is correctly predicted for all three cases. Locally, pressure is not, but overall, the loading is quite fine. So this is the comparisons between for the impulsive case, comparison between quasi-static and hydroelastic simulations. So in this animation, on the right-hand side, we have the quasi-static simulation, and the left-hand side we have the hydroelastic simulation. As you can see, if you apply directly quasi-static pressure without accounting for the dynamic, your structure will probably be broken, and your structure response will be enormous. Because when you do quasi-static, your structure response is more or less proportional to the pressure. But when you use hydroelastic model, on the left-hand side of this, you see that the deformation is much milder, and because these high pressure peaks are absorbed by the dynamics of the interaction. So the comparisons between analytical and numerical results are on this graph. So even if it's good to see that even for small dead-rise angle, the CFD obtain quite reasonable results, even if they are they need to be filtered at the end, because there is quite a lot of oscillations in terms of the CFD loading and the response. Actually, for this case, when you deal with quasi-static. As I said, this is the green part of the curve. Then your response, which is here presented in terms of maximum deflection, is directly proportional in some sense to the loading. So this is the case where you have the kind of dynamic amplification. So in this case, we need to take into account the dynamic amplification, but the difference between quasi-static and dynamic is not so huge. So these dynamic amplifications goes up to here 1.15 or 1.18, which is not, say, huge. If we miss something, if we use quasi-static simulation here, and then we will miss maybe 20% of the response. But when you are in the impulsive regime, you can be completely wrong. And finally, this is the quasi-static response. This point, when the ratio is around 3, and then the comparison between quasi-static and already comparison between the purely numerical and analytical results are good, and there are some differences between in terms of how to say, they compare well with each other, but there are some differences between quasi-static and still some differences between quasi-static and hydroelastic. This is the summary of all 21 cases and all type of simulations we did, and without going much into the details, the idea is to show that using the hydroelastic coupling method between purely numerical CFD method and structural finite element method can properly capture this dynamic amplification curve. Of course, this is not this is the dynamic amplification factor, so we cannot say that the results are I mean, it's difficult to validate the results compared to the Wagner approach, because Wagner approach is too much idealized, but it is good to know that even though the CFD properly capture all these different regimes in terms of this dynamic amplification. So in total response, which is something we are interested at the end, is compared to analytical and numerical, is reasonably close. I mean, analytical and numerical results. The dynamic amplification, of course, cannot be perfect, because we are dividing the things which are not the same. But the good point is that using the purely numerical method, we are able to reproduce the total response properly. This is in terms of the deflection, and this is in terms of the strain, which is the second derivative of the deflection. So that's actually the presentation of the results and the methods. So these are the conclusion and some discussions. So it is good to see that pure CFD and finite element method coupling can simulate all the different hydrostructure interaction regimes. There were quite some problems when we started to do this work and some convergence, but when you fine-tune your model, you are able to do it properly. So the difference in the pressures at the end does not, which were quite huge for very, especially for impulsive conditions, where difference were very big, but in terms of structural response, this does not matter. And that was one of the goals of this study, to show that the maximum pressure does not matter. So modal and direct approach show sensibly the same results, which is also good. That means that because one of the goals is to use this direct approach to study nonlinear structure response. Because modal approach, you can use it only if your structure response is supposed to be linear, while the direct approach, you can use it for any type of simulations. These two numerical procedures for capturing the free surface, GFM and no GFM, they show some differences, but they both reasonably well produce the final results. So in this present case, we can say that there is no difference and there is no benefit using the ghost fluid model, which is somehow a bit more complex to put in practice, apparently. So all the numerical coupling procedure converge properly in terms of the structure response, not the pressure. Pressure can be different several 100%, but that does not matter for the structure response, which means that the pressure should not be used as a single parameter for evaluating the structure response. In these situations, we should not talk simply about the maximum pressure, but that's somehow the only thing we talk in practice, and that's not really correct for these applications. So on CFD side, we have quite noisy pressure signals in both quasi-static and hydroelastic simulation, but this noise is somehow filtered by the structural dynamics, which is good, which is also expected, but that means that even if we have very noisy pressure and very high peak, locally high peak pressure, the final result will, in terms of stresses, will always converge. For this particular case, we also saw that the compressibility does not play an important role, and hydroelastic analysis, which is something a bit more complex and more costly, it has been shown that it takes not so, actually 3 to 4 times the CPU time necessary for quasi-static simulations, which is not huge. So we can afford using this dynamic coupling without significant cost. So this is about I think I will stop. This is one, just say one comment. Sometimes due to the difficulties of coupling the loading and the response side, there are some methods which are proposed sometimes in the literature, which is based on so-called quasi-dynamic approach. Quasi-dynamic approach, what that means? That means that we calculate we pre-calculate the loading, means pressure distribution over the wedge, and we calculate dynamic response of the structure without as a quasi-static, as a structural dynamic response, but without taking into account the interaction, which means basically that we do not account for the effect of aided mass. So in the cases where the aided mass is not important, this quasi-dynamic or full dynamic and full dynamic approach can give the similar results. But in this present case, where the aided mass is much bigger than the genuine mass of the structure, the results are completely different. So that means that we cannot use this quasi-dynamic approach in this particular case. Okay, so this is my presentation. I think I remain within the time. Sasha?
Yes, thank you.
If you have any question,
yes,
please be free to ask. And comment, whatever
yes, we have enough time for questions. Thank you very much. It's a very good presentation, very clear, and also the practical side is shown, which is a little bit more in particular, it's important for us that we understand what we are doing in terms of our research, because in research, in mathematical research, we write an equation, doing simple calculations and make more or less reasonable figures or pictures, but then it's a big problem what it means for real life. So
Yes.
that is doing these seminars and cooperating with the people who are doing practical work. It's important for us to understand actually what we are doing.
Yeah.
In that sense. Yeah. So I'm using my say privilege. In some sense, it's not privilege, but kind of privilege to ask first questions, and then the floor will be open for other questions. First of all, it's about dynamic amplification factor. How it's defined? I understand it can be defined differently. It can be defined as a ratio of maximum stresses or ratio of maximum deflections, and also what means what means. I believe it's dynamic with respect to quasi-static response, right? So what means quasi-static? Because as you showed in slide 35, quasi-static is also can be understood differently. So
Yes.
please.
The quasi-static response is obtained when you simply you calculate the pressure on as if the body was rigid, you applied on the structure and you calculate the response. There is no dynamics. There is no dynamics of the structure at all, and that's the reference quasi-static result. And hydroelastic response is the full interaction, as in your analytical work or equivalently in this numerical work. And the final results, when you do coupled and uncoupled, quasi-static and hydroelastic, you obtain structure response in terms of deflections, stress, or whatever. So what I show was the dynamic amplification factor defined as the ratio in between the deflection, dynamic and quasi-static, but also strain. So both are very similar. So because the strain is a second derivative of the deflection, and in some sense in some sense the behavior dynamic amplification is the same, similar. I would say not exactly the same, but similar.
Okay. So thank you. As I said, the slide 35 about importance of edit mass is rather impressive. So it's good to see such. It's very last slide. 35. Yeah.
In this case,
it's very convincing that the coupling should be done. One question, in some sense personal, because it's bothered me a lot, is about, the details of the pressure are not important for structural response, but still there is something from the pressure which is important. What's that? Is some integrals or like a pressure impulse or something else? So it's still not clear for me. Do you have any ideas or feeling what this could be?
Well, what plays the role is the integral of the pressure, means in time and in space. So the impulse in time, and also the structure, the area of the structure which is affected. Because for this particular case, and in general, I would say also from the model test, larger the peak, shorter the rise time, and smaller the surface which is affected. So the structure response does not respond locally; it responds globally. So that's why the history of the loading and the affected surface matter together with the more than the maximum pressure, I would say. So the maximum pressure, that's something not really new. I mean, people in practice are talking about this, especially in the work of Faltis, and we should never consider only simply, I mean, the maximum pressure. We should not talk just pressure. When you have large pressures, there is interaction, and these large pressures are real. They exist when you do model tests, when you do CFD, analytically they are predicted, so they exist. You can have 100 bars pressure locally, but it doesn't matter necessarily for the structure response.
Okay, I see, thank you. Any other questions, please? Just unmute your microphone. You can, yeah, Frank, please. Frank.
Yeah, very nice talk. There are some interesting jets in the free surface shape, or jets or spikes. I'm wondering, did they require much extra grid refinement to capture numerically?
Yeah, actually, I think they require, if you want to properly catch the jet, you will need to refine. But the point is that these jets are, if you want, are not the main quantity which is relevant for the structural response. You see, so even if you do not capture them very well, your structural response will be fairly well reproduced. But indeed, the CFD, they always have this problem of capturing the free surface interface, and if you want to capture it better, you need to pay in a meshing size and the CPU time.
Yes. Okay. So your maximum resolution was corners, I guess. Is that right?
I'm not sure I can properly answer, but there is the maximum resolution we took. It was 300 elements on the wedge, on the which is quite big. I mean, we cannot in practice, maybe we cannot afford for this in 3D cases. It will go too much, and but we have seen that this such a fine mesh is not. I have some other slides which I didn't show, that it is not necessary to have such a fine mesh, but we need to do it to check the convergence. So at the end, I think we were working with even 64 elements per the wedge length is enough in terms of the structural response. The pressure peaks are completely different from one mesh to the other. Because more you refine, I think in CFD, more you refine, more the pressure becomes big. But in this case, it doesn't really matter. I mean, you will, for this, some cases you will never maybe converge in terms of pressure, but it doesn't matter. That's the point. That's the kind of message I was.
Yes, some sort of, you want some integral property.
Integral in time and in space.
Yeah. So that is the in these problems of hydroelasticity in particular, but in other problems, I believe as well. We also need to define what we mean by convergence. So the convergence here is convergence in terms of structural response. Right? Is it right?
Yeah. That's right. That's right.
Yeah. So if we are, if we formulate problem differently, if we say, okay, we want to describe all fine details of flow everywhere, then that is another problem even.
Yes.
Right?
Yes.
So the problem is not just kind of equations, but also we need. There is a name. It's like a solution-oriented method or practical-oriented method or something like this. So we need to specify what we want from this problem. And to which accuracy, if we calculate deflections, then we are concerned with convergence of deflection. If we are concerned with the flow, why not? Right? Or with the jets, for example, with maximum pressure, with fine details, what's happening in that pressure, then it's another problem. It's just another problem.
Yes.
So we need to use different tools even. Right?
Yes.
So that is, in particular, that is message, as I understand from this presentation.
Everything depends what you are looking for. Yeah.
On the other hand, as you said, it's not necessary to resolve, say, jets or flow accurately, but we still need to resolve kind of properly.
Yes.
Right?
Yes.
So we can cut jets, we can neglect something, but we should done it kind of accurately in some sense, right? So not arbitrary, at least.
Yes.
That is right. Any other questions, please? Any other? We still have time. Please use this chance to get consultation from an expert. Anything? Sean, please show yourself and ask your question. Sean.
Okay. This is Shan Wang from University of Lisbon. Thank you very much for your very nice and interesting presentation. So the first question is how the OpenFoam CFD simulation was coupled with finite element modeling.
Yes, that's the big part of the work was dedicated to that. So this is the coupling scheme which is shown. So there are some iteration procedure. You deform in order to properly capture this added mass effect, you need to deform your mesh consistently at each time step and to resolve your coupling motion equation in this way. So I mean there is iterative procedure at each time step. And in details, it's
I know there are a lot of details, but I mean, did you develop a finite element code in the source of OpenFoam, or you coupled two different solvers?
In this particular cases, we captured two different solvers.
So that's for the finite element solver is Dyna2, right?
Yes. The finite element.
These two solvers are connected, are coupled.
Yes, with OpenFoam, yeah. It's coupled through the interface files. There is no full integration of one software to another. That's what is planned to be done in the future because it will be much more efficient. In this case, the efficiency was not the first objective. The objective was to show that we can do it.
Yeah.
Okay, and how about the consistency of the mesh in different solvers? Is the mesh resolution in OpenFoam is the same as the one in the finite element modeling?
The mesh resolution in CFD in OpenFoam is much finer than in the finite element model. So in finite element model, I said that there is 20 finite elements, but on CFD side, we have between 60 and 300 elements. This is necessary to properly load each finite element. When you use the modal approach, you can live with less maybe elements, but when you use the direct approach, you need to have at least several CFD meshes over one finite element.
Okay, because I'm also using OpenFoam for word entry problems, and every time when I submit my paper to journal, and the reviewer always requests finite mesh to get the maximum pressure. So in your presentation, you mentioned that the maximum pressure is not important.
Yes.
So does this mean that we can apply coarser mesh in this coupling?
Yes.
If it's important, why don't we just use a coarse mesh in CFD to save a lot of computational time?
Yes. If you use full coupling, then you can afford using the coarser mesh because this high pressure will be filtered by the structural dynamics. But if you use quasi-static, approach, then it's not good, because your pressure, I mean, the structure response is directly proportional to the pressure. So your result will be wrong. If you use full coupling, then you don't really care, in some sense, about the resolution, because whatever the small errors, they will be filtered by the structure. While when you use quasi-static, there is no filter. So you just proportional to the pressure. If your pressure is noisy, your structure response will be noisy.
Yeah. So in my previous studies, I concluded that if we are interested in the structure deflections, we can use a relatively bigger mesh. If we are interested in the pressure in the fluid field, we can use the finite mesh.
Yes, that's true.
What I concluded before.
Yeah, that's true. That's right. That's in line with the conclusion that we had. Yeah.
Okay, I have another general question.
Yes.
So in your presentation, you mentioned in the conclusion the numerical solution is agree well with the analytical solution. But I believe that for analytical solution, we can get the deflections in the middle of the structure in several minutes or several seconds. So if these two methods agree very well, what is the advantage to use the coupled numerical solutions, which takes a lot of time?
Yeah, the idea here was to validate CFD, because the wedge impact, this it's kind of academic case. You never, in practical applications, you can not, as I show, these are the practical applications that we are targeting. You will never have pure wedge impact. You understand? You see, this is the, okay, the impact in nature happens with the very different geometries, and you cannot approximate it by the wedge impact, so you need to use CFD. You cannot have analytical results for these complex geometries. So the idea is to validate CFD on simple geometry and then use it for very general geometries. That's the idea. We cannot straightforwardly use the CFD without validating for these different regime, impulsive, dynamic, and quasi-static. Once we validate them and once we understand what is important in this coupling, we can safely use it for general application. That was the idea.
Mm-hmm. It's yeah, just a comment. We have question. Thank you very much, and your question is a little bit philosophical question about how to do research and what the relation between the theoretical research, computations, and even experiments. Because I remember in that. Mirek Kaminsky, he used analytical solutions to calibrate his pressure gauges. So that is strange, right? But in some ideal conditions, which can be reproduced numerically or experimentally, we believe, and it's happening, that the theoretical models work fine, but not always. And we need to know which function, say, played by theoretical models or simplified model, and what the computation model are doing. So there is the, as I remember, reports from BV about kind of methodology of the using CFD, right? So kind of that to cover the whole field by simple but more or less reliable computation, identify the, say, like hotspots, and then go there with the CFD and with more detailed analysis. Yes. Something like that. So that I remember. I believe this methodology evolved from the time when I saw it, but yeah, it's still philosophical. Yes, not philosophical, but it's fundamental question of research. How to believe finally to the result of the research. Actually, we should believe to. It's just like all our results are. They call this truth-like results, and they just increase level of our, say, belief or our trust to some results, right?
Yeah.
But no model can give certain answer, and no calculation can give certain answer. So that is, even we are talking about mathematics and mathematical calculations, but actually the function of, or not function, but the useful use of mathematics is rather, mathematical results are rather limited. Yeah, so, but still important as always, as anything. Yeah.
Yes.
So I'm talking to my Claudia. Could you please?
Yeah,
Claudia. Yeah.
Let me thank first Shime for the very interesting talk, and then also Alexander to invite me to attend this talk. And I have just a question for you, Shime, which concern the, I mean, as you say, the added mass is extremely, the proper evaluation, the added mass is extremely important when you are in the impulsive and in the dynamic stage, regime. So to the purpose, I mean, and the added mass is strongly dependent on the actual wetted surface on the body, and how this one, the wetted surface, changes in time.
Yes.
So my question is the following: how this one? I mean, how is important? I mean, I perfectly agree with you that is not important. Is not definitely important. The detail of the hydrodynamics, but I would have your opinion about the proper evaluation of the added mass that depend on the real evolution of the wave along the body. I mean, of the water surface along the body.
Yes, the added mass indeed depends on the wetted part. That's true, but this is correctly taken into account in the both in the analytical and in the purely numerical model. So now everything depends when the maximum stress happen. So in some cases, the maximum stress happen once the wedge is completely wetted, in which case you have a full added mass. In some cases, it depends. It happens before the entrance, before full immersion. So that depends. But once you have your, your method which is correctly taking into account this, then you don't care. I mean, the added mass is automatically taken into account together with the fact that it changes in time.
Yeah. No, but what I would stress is that probably, but this one depend on a good accuracy in the hydrodynamic solver. I mean,
yes.
I mean on both of them because they are coupled, and so they. But anyway,
yes.
the hydrodynamic solver must be probably And then the second question concern. I mean, if I have time, the second question concern. I mean, the big problem about the repeatability. I mean, this one is particularly true during the experiments about the repeatability of the experiments, and so usually the dispersion in the measurement data are really high. This one is, I mean, is definitely true. Probably it's impossible, at least my experience, to measure in a proper way the pressure. But I mean, from our experience, is also quite large. Is much less, but anyways, is in any case as absolute value as quite large also in the structural response of the body. So what we found, and I mean, was I'm also in the advisory committee of another project in Norway, and also there they observed that in any case the structural response has a quite large dispersion in the data measurement.
I understand that the local pressure can be not repeatable at all, but if the structural response is not repeatable, that's more dangerous, I would say.
I mean, is slightly more repeatable. I mean, in the pressure, I found, for example, we found in the past that the error can be also 100%. So it's completely random. I mean, we cannot say nothing. For the structural response, we have an error that is definitely less than 40%, something like that, 40, 50%, but it's still large.
It's still large. Yeah. That's I don't know. I mean, if the geometry of the impact is respected, there should not be much differences, but theoretically, but you never know.
Sure. Because the idea is exactly what you say. I mean, the structure should be a low-pass filter.
Yeah, that's true.
That's
the point.
Okay.
Yeah.
Thank you, Claudio.
Shimi, you could remember in that project I mentioned at the beginning, tools. I believe in that project there were blind comparison of impact.
Yes.
Experiments were done by, I believe, Hyundai, and the calculation by Hyundai were very close to the experimental results, but then it was blind prediction. And other companies, including BV and DNV, submitted their predictions, and they just were put in the same picture. And indeed, as Claudia said, they were very different. In some sense, as I remember, without knowing the result, it's difficult to compute right values.
That's always
But that could be I don't know. This could be not a problem with the impact. It could be a problem with the structural solver, and which is also should be investigated in terms of sensitivity of the stresses to something. Because there could be the kind of local natural frequency of structure vibration, and
sure, you are right.
On
probably
that,
you are right.
It could be anything, right? But to investigate the structure is very complicated, right? So the structural response to a certain load is nice, but to another load it could be just disaster, right? So how to do this, that is important, I believe, for design of the structure, right? So it could be, what Claudia is pointed about the sensitivity of the structural response. We need to possibly we need to separate these two cases, the loads and the responses. Any other questions? We are a little bit behind the schedule, but or any comments? Any comments? That coupling, as I saw it, it's written. Coupling is implicit, right? So that means it's very expensive coupling. So it means that you calculate that I don't know Jacobian at each time step, and to solve the problem. So I believe it's the very expensive. So if you, as you mentioned, after that successful work you presented, if BV or somebody else decide to make coupled software, everything at once, finite elements and the hydrodynamic, that it could be very helpful, I think.
Yes.
Okay. Thank you very much. And it's first of all, thank you to our speakers, and thank you to our discussers. I stop recording in a few seconds, and the file, if you want that file to get, I can send you. And University Zambia is working on making a YouTube channel for our seminar. Then, once it will be ready, then all our presentations will be there for public. I hope they will be open for anybody in the world, and everybody could learn about the dynamic amplification factor and importance of structural response, but still problems even with the structural response. So that means that we got many questions, many answers, but we still with those answers we got even more questions to answer. Yeah. So yeah, thank you very much, and I close the session. Means I start to download. Sorry. Okay. Yeah, I believe I stopped just a moment. Stop. No, no, I didn't stop. Okay.